Good evening, everyone. Welcome to the live session for the course Polymer Reaction Engineering. In today's live session, we'll be discussing some sample problems which will help you solve this week's assignments. Uh, in today's live session discussion, we'll be learning more about emulsion polymerization process and its different parameters and aspects. So, starting from the first question. First question is, particle nucleation will occur due to both homogeneous and heterogeneous nucleation mechanisms if choose the correct options. So homogeneous and heterogeneous nucleation mechanisms are part of the emulsion polymerization process. So and operating under uh, particle nucleation occurs in both heterogeneous and homogeneous way, and its rate is the rate of nucleation is controlled by the radical entry into the micelles and the number of micelles inside the reactor. So with respect to solubility, the monomer should be water soluble for homogeneous nucleation process, and the concentration of surfactant should be high enough that the micelle formation can take place because the rate expression, uh, if you take a look at it, the rate expression for nucleation is quite dependent upon the number of micelles inside the reactor. Okay, and total polymer NM divided by the volume of it. So here you can see that the rate coefficient for radical entry into the micelles and the number of micelles inside the reactor. So the concentration of surfactant should be high enough that the micelle formation can easily occur because this is controlling the nucleation mechanisms in the emulsion polymerization process. Moving on to the next question. What factors affect the molecular weight distribution in emulsion polymerization process? So in emulsion polymerization process, what are the factors which affect the molecular weight distribution? So as we've seen in the previous session that the kinetic length of the polymer chain undergoing initiation and propagation step is very much detrimental for the molecular weight distribution in any polymerization process, more so in emulsion polymerization process. So the initiator type and the concentration will be determining the kinetic length of the polymer chain. The, on top of that, the temperature and monomer concentration. As we have seen that because of the change in temperature, the kinetic length also changes and the polymerization rates differ. So because of that, the initiator type and concentration, along with temperature and monomer concentration, affect the kinetic length of the polymer. So because of this, these three factors are very much important in determining the molecular weight distribution during an emulsion polymerization process. Uh, Next is a true or false statement type question. The advantages of operating emulsion polymerization reactor under limited monomer supply maximizes the production rate and yield. So the advantages of operating the emulsion polymerization reactor under limited monomer supply maximizes the production and yield. So the advantage is that monomer starve process won't get inhibited as the inhibition reaction is minimum. So that is one of the advantages of operating emulsion polymerization reactor under limited monomer supply. It wouldn't uh, it wouldn't be affecting the production rate and yield, but the parameter which is affected more is the copolymer composition. Operating under limited monomer supply will help to control the copolymer composition and feeding the monomer mixture at lower rates than the rate of polymerization will be the determining factor for uh, controlling the copolymer composition. So this statement, which says that the advantages include maximization of production and rate and yield, are false. Because the only advantage with monomer starved reactions is that inhibition would be strong. So in reduction of inhibition is something which is the only advantage here. Moving on, the amount of surfactant that is dissolved in the aqueous phase, SW, in case of heterogeneous nucleation in emulsion polymerization can be obtained in terms of performing the material balance for surfactant. Since we have seen in the previous question that surfactant concentration determined by the number of micelles in the reactor is a very important parameter in uh, in determining the heterogeneous nucleation in an emulsion polymerization reaction. So, performing a material balance on the surfactant itself will help us determine the emulsifier in the reactor Sp mole and total surface area of the polymer particles. So, the common expression for this, if you would have seen the lecture notes, you can see that the common expression for this is SW is given as is dependent upon Sp minus A B star by AS. So the parameters in this is that this is the amount of surfactant which is dissolved. So we are performing a balance, material balance on the surfactant here. This is the amount of surfactant dissolved, and this is the total amount of emulsifier. Total amount of emulsifiers. Emulsifiers. Total amount of emulsifiers will be determining the amount of surfactant which is getting dissolved, and we are subtracting the total surface area of the polymer particles. Total surface area of the polymer particles. So emulsifiers will be putting the surface area of the polymer particles. So we are keeping the as the greater surface area, more emulsifiers will be spread around on the large surface area of the polymer particles. And in the aqueous phase, forming the micelles, aqueous phase forming the micelles, the amount of surfactant dissolved is dependent upon these parameters, and the parking area is right here. So this is the equation which governs the material balance for a surfactant and the amount of surfactant dissolved in aqueous phase, which is helpful for formation of micelles. So that will be the first expression right here. Moving on to the next question. The rate formation of particles by homogeneous nucleation is the rate at which the oligoradicals growing in aqueous phase exceeds the maximum soluble length. So this is a straightforward question for the rate formation of particles by homogeneous nucleation uh, in emulsion polymerization process. The oligoradicals growing rate in the aqueous phase exceeds the maximum. When it exceeds the maximum soluble length, it will give you the rate formation of the particles. On top of that, the critical length depends upon the composition of the oligoradicals. So this determines the rate. So this is related to the rate expression for the homogeneous nucleation process. So yes, as the maximum soluble length uh, exceeds the aqueous phase, it will give you the rate formation of the particles. So it's true. Next question. What are the ways to remove the residual monomer? So residual monomer is a big problem in polymerization process. As the polymerization process ends, we can see that some of the monomers are they do not undergo any initiation, because of which they don't turn up into the polymers. So these residual monomers, what are the methods to remove them? Since we need to get rid of them. So the options are post-polymerization process, devolatilization process, controlling the rate of polymerization, introducing fresh radicals at intermediate stage of polymerization. So starting from the first one, we have post-polymerization process. In post-polymerization process, it consists of inserting fresh radicals to generate inside the system to generate new polymers. That is, the remaining monomers can again be polymerized by introducing a fresh set of radicals at the end of the polymerization reaction. It's like having a secondary polymerization reaction at the end of the main polymerization process. So that will be helpful in converting all the unconverted monomers, residual monomers basically. So an example of this would be that the water-soluble redox systems are preferred because high radical flux can be achieved there at the end of the main polymerization process by introduction of fresh radicals. Second one, so this is one of the methods for removal of residual monomer process. We are not removing them, we are basically converting the residual monomers to new polymer by addition of fresh radicals. So next is the devolatilization process. Devolatilization process is helpful on volatile organic compounds present inside the polymers, and this is basically a mass transfer operation in which what happens is the diffusion of the volatile organic compounds uh, occurs to the surface, particle surface, and next from the polymer surface they diffuse into the aqueous phase. And after diffusion into the aqueous phase, they transfer to the gas phase. So because of this, what happens is unconverted residual monomers are removed, and as the surface area of this operation increases, in case that the polymers which are formed during the main polymerization reactions have a high surface area. So as the surface area increases, more volatilization can occur. And this process can be carried out by flash volatilization process. So devolatilization process is also a major process in removing of the residual monomers. Controlling the rate of polymerization process won't help in any way in removing of the residual monomers, since this is a phenomena which occurs during the polymerization process, control of the rate of polymerization, and not at the end, which is removal of residual polymer. Introducing fresh radicals at the intermediate stage of polymerization. Now, introducing fresh radicals at intermediate stage of polymerization uh, won't be helpful in intermediate stages, as the uh, polymerization process is underway, and at that point, the formation of uh, any new species might get hindered because of introduction of radicals at this intermediate stage. Moving on to the next question, we have simple true or false question. Linear emulsion polymer can only be formed if the average number of radicals per particle in bar is greater than zero point 0.5. So if you studied the lecture notes, you know that linear emulsion polymerization does not have any specific average number of radicals. So based on that, you can say that this is false. How are linear polymers formed in absence of chain transfer mechanism? So linear formation of linear polymers occurs. Linear polymers are polymers which are just attached to the other polymer chains on either side without any other functional group attachment. So without in absence of chain transfer mechanism, presence of a functional monomer unit will be the one which will decide how the polymers are linearly formed. So if you have a bifunctional monomer unit, which is having more than one active site for the polymerization to occur, there might be some slight branching. So linear polymer won't form there. But in presence of a monofunctional monomer unit, polymer chain formation will only occur on the either side of it, and then the propagation will occur from that point. So basically, because of that, the presence of monofunctional monomer unit is important for formation of linear polymers. Which interfacial aspect controls the polymer migration process? So, in polymer migration process is polymer migration process occurs after the after when the newly formed polymers, which forms on the periphery of the polymer particles, when the radicals attach onto the outer layer of particles and cause polymerization. The increasing concentration of newly developed polymer chains when they phase separate will lead to formation of clusters. Now, what happens from that point onwards is that polymer reaction occurs at both clusters. Like if you have a polymer cluster like this small polymer cluster, the polymer it will happen both inside the cluster and the polymer matrix and the surrounding polymer matrix around. It will be occurring inside the clusters also and inside the polymer matrix also. So due to the large interfacial area of the polymer involved, there will be a imbalance in the forces, surface forces, which causes thermodynamic imbalances. Because of this, the polymer migration occurs, increasing in cluster size. And the forces which are responsible for this, the surface phenomena, are van der Waals force of attraction and repulsion, and the resistance to flow, which is occurring due to viscous drag. Since the polymerization process occurs and clusters are formed, what happens is that the flow of these clusters will be hindered since viscosity is increasing. So viscous drag will always play a role in this. And then van der Waals force in presence of other clusters, what would happen is that either like attractive forces will bring them together to form a bigger cluster, or uh, or repulsive forces will drive them away inside the polymer matrix. Uh, Radical attachment on the outer layer of a new polymer will only lead to formation of new polymer on the periphery of the particle. So this won't have a role in determining the polymer migration process, interfacial aspect of polymer migration process. Next one is the question for a Covert-Taylor reactor system. How can Taylor number be improved in Covert-Taylor flow reactor? Now, Covert-Taylor flow reactor is a concentric flow concentric flow reactor. If you have seen the lecture notes, you know it's a concentric flow reactor where the flow is occurring between two concentric cylinders. So in that case, what happens is that uh, formation of vortexes might take place. So that is determined by the Taylor number, which describes the inertial forces due to rotation with respect to the viscous forces of the fluid involved. So as the polymerization process goes on, carries forward, what happens is that the viscosity inside will keep increasing. Okay, so changing the temperature inside the reactor won't help the process much, as it will be driving the polymer polymerization process faster and result in increase in viscosity further. But modification of the cylinder geometry, which will help in basically controlling the vortex formation and vortex stabilization channel. So what happens is that once the vortex formation occurs inside the concentric cylinders, the best way to have a homogeneous vortex formation inside the annulus region is that we have a conical structured outer cylinder. Conical structured outer cylinder, what it will do is that Taylor number can be improved in this case how the vortex formation is controlled. So vortex formation would be stable enough, and because of that, the Taylor number can be controlled in that case. So controlling the vortex formation will basically be a subpart of modifying the cylinder geometry itself, which can help in uh, improving the Taylor number of the forward Taylor flow reactor. So thank you for attending this session, and I hope that the questions we have discussed here will be helpful for you in solving your this week's assignment. Thank you.